Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Where tonight we're going to take some time and think about Pi. It's coming up soon, and we'd like to give you some activities that you can do with your students. My name is Mike Houston, and I'm the moderator for this event. I teach algebra, calculus, statistics, and chemistry at a school just outside Pittsburgh, where I use TI technology to make tough to teach, tough to learn concepts accessible to all my students. And with us tonight, we have Corey Bennett and Anthony Melly. Super excited to have these guys with us. They're going to do a little more of an introduction whenever they start presenting. We're going to be using that chat window tonight. Some of you have already started with where you're joining us from. I just was thinking what maybe you could use the chat window. What's your favorite pie? I know what mine is. I'm not a huge fan of pie actually, but Oreo cream is my favorite for anyone that wants to send me any. We're also going to be recording this, and we'll be providing a link to the event certificate of attendance at the conclusion of the event. So Anthony, take it away, sir.
Thank you very much, Michael. Okay, welcome everyone. So happy to be here with all of you tonight. I'm going to let Corey introduce himself.
I'm Corey Bennett. I come to you from just outside of Salt Lake City in Utah. I was looking for some Utah people in the chat, and we got the East Coast covered, which is really good. But I'm looking out my window, and we have a lovely sunset tonight. It's a cloudless blue sky and a chilling 42 degrees. It's wonderful. I've taught mathematics for about 40 some odd years. I taught in the middle school and 7th grade math through college and so forth. Right now I'm teaching with New Ames and the Northern Utah Academy of Math, Engineering, and Science. I also do some teaching and training for Power School, which is a student information system. I was one of the implementers way back at the turn of the century. This is my lovely wife, Shelda, that's in the picture with me here. And we are the grandparents, I hope you're sitting down, of 24 grandchildren. Now, you may not remember what we do in a presentation, but if you see me again, I bet you remember my 24 grandkids. Thanks, Anthony.
And my name is Anthony Melly. I teach in the Toronto District School Board. Corey, the sun went down here a good couple of hours ago. We're in the Eastern time. But yeah, let's see, this is my 29th year teaching. And in most circles, that puts me among the, the most experienced. But getting together with Corey to do this was humbling because he's been doing this a little bit longer than I have. I teach at Lakeshore Collegiate Institute. I've been there for about 12 years. And I've got a little factoid at the bottom of the screen there. I have never celebrated Pi Day with students. It's a bit of a half lie because I have celebrated ahead of Pi Day. But here in Ontario, where I live, we always have our spring break, our March break, the same week as Pi Day. So I've never yet been in school during Pi Day. But Corey and I had so much fun noodling around with different activities. We're really looking forward to sharing some of them with you today. So this is just an overview of what we're going to be covering. We're trying to cover different platforms. So if you're an 84 user or if you're a TI-Nspire user, you're going to see some different things that we're going to try. And we're going to offer some suggestions for different ways that you could approach things as well. Please make sure you stick around till the end because there will be a draw for a handheld and you've got to be here to win it. I'm going to start with an activity that we found on the TI website, and I'm going to show you exactly where to find that later on. I really like the activity because it has great visuals. I've done an activity like this with actual circular objects and had my students measuring, and so much of the activity was busy with students trying to figure out how to measure circumference or measure the diameter so that they could do the calculation. Whereas this one, it's kind of given to them as a delicious photograph, and the students just have to sort of, figure out what the diameter and circumference are for each of the different circles in the picture and put them together. So if you're a TI-84 user or even a TI-83 user, a lot of this is going to seem familiar to you, but I just thought we'd start off with this. So I'm going to fire up my SmartView emulator, and I'm just going to maximize the screen here. And so the first thing I'm going to do, well, we're going to go to stat and we're going to load all the data. Now, I've already preloaded that, but we can show the students how to enter. The first column would be the diameter of the different circles, and the second would be their circumference. And even before we start to get too fancy and looking at graphs or other manipulations we're going to make here, I want to just get them to simply divide these two numbers on this row. So I'm just going to type in here on this cell, the first row of L3, I'm going to type 15.7. You can see it at the bottom there, divided by 5. And just get them to divide that. And then I'm going to go down the row and just get them to divide the circumference by the diameter a few times. In fact, I might even get them to do the entire row like that. And some of you might be screaming at me, but Anthony, you can just type in a formula. And I know you can do that, but I kind of like the repetitive nature of having them calculate by dividing those two numbers, because I really want to anchor that concept. Now, if you want to do this a little bit quicker, of course, we can go up to where it says L3 equals, and we can type in list 2, L2 divided by list 1, and it'll populate all those. We can do that for our purposes because we know what's coming here. But what I want the students to discover is that, hey, that ratio is always the same. And how did I do it? Well, I did it so many times, I'll never forget now, right? I'm dividing the circumference by the radius. But we can do a little bit more with that. We might want to graph it. If I go over to graph, of course, I'm not going to see anything yet. If I type second y equals and go to the stat plot, I'm going to turn on that first stat plot, it's a scatter plot showing my two lists. And well, if I graph that, I don't see much unless I zoom. So I'm going to go to zoom stat. Here we go. And we see that all those dots are lined up really well. Wouldn't it be nice to do a regression? Why don't we try that? We'll go to stat, and I'm going to glide over to where calc is for the calculations. And we're going to choose to do a linear regression. And before I run down and hit calculate, I'm just going to back up a tiny bit to where it says store the regression equation. I want to store this equation. And a bit of a shortcut for you is we can press alpha and then y equals. And there's some shortcuts here. One of them is to the y1, y2 functions. And so I'm going to ask it to store the regression equation in equation y1. And then I'm going to ask it to calculate the regression. So here we go. It did the regression. It's got the A and B parameters. And now I think I'm ready to graph it. So let's give that a try. And this time when it graphs it, it puts the line of best fit, or the regression line directly through every single one of those points. So that was kind of, that's kind of a fun thing. And then you can ask them, well, what is the slope of that line? And maybe they know what the equation for slope is. They'll see the 3.14. And that's, I think it's a nice way of introducing it, especially for students who don't know what pi is. And that actually brings me to kind of an important point. The thing I really like about this activity is when I ask students like if I grade 9, my students have already been introduced to pi. I don't usually get to introduce it to them for the first time, but I'll often ask them, what's pi? And they'll tell me all kinds of things. And I'll say, okay, but why is it important? And often they don't know. They'll know that pi is an infinitely expanding sequence of decimals that never repeats and never terminates. They'll know all kinds of things about pi, all kinds of factoids, but I really want them to know this. I just want them to know this one simple thing. Pi is an important ratio, and it helps us calculate circumference from diameter or diameter from circumference, or just to understand that it's simply that ratio. It's a little bit more than 3. Frankly, I'd be okay if they just remembered it was a little bit more than 3. But all these other facts, hey, we have a lot of fun with them, but let's not let them forget that really fundamental thing. Corey's going to take over from here. He's going to share an activity that involves Turtle Python.
I thought, what better way to celebrate Pi Day than to do Python? I know it's kind of a dad joke, but when you're a math teacher and a dad and a grandpa, you get those kind of jokes. It's just, Now, Python, I hadn't had a lot of experience with Python. I saw it on my calculator and I thought, okay, cool, this is a programming language. But I wanted to explore a special module for Python. It's called Turtle Python. And Turtle Python takes its origins from Logo. You can see here that Logo was created back in the 60s and they used it in the 70s. And it's a really nice, simple language that you can even teach elementary kids, middle school kids, introduce them to some programming if you have these types of calculators. So what this does is this logo, or the turtle, is just a little, turtle that's sitting there, and it goes forward and back and left and right and, follows some of the commands. Real easy to put together. So let's show you what it does here. First off, we need to know where to get it. If you have the TI-Nspire CX2, it has Python on it. And what you need to do is to download this turtle module. And I think Anthony has put that into the chat for us. But there's also that QR code you can scan. And it will direct you to where you can download the turtle module. It doesn't come ordinarily with it, but this will get you to the right place. And it's also available on the 84 plus CE Python. Again, you have to have Python on your calculator or it won't run this. So let's show you what it looks like when we get that. You've got the QR code. By the way, these slides are going to be available at the end of the presentation. So if you don't get your camera out really quick and click on that, you can also pick it up in the chat as Anthony shares that. Okay, what I want to do is to take this Python turtle and I want to make a polygon, right? And I want to make a polygon with enough sides that it will approximate the circle. So that perimeter would be the circumference, and the diameter, or the diagonal, sorry, would approximate the diameter of the thing. Okay, so let's go in here and take a look at that code. I'm operating from the CAS calculator right here, but you don't need to be in CAS. We're just going to go New, Python, New, and I'm just going to make a really simple program called Square. Okay? And there it is. You can see the Python logo right here. But in order to invoke the turtle commands, I have to load the library. So that means I go to Menu, More Modules, Turtle Graphics. Now at this point, if you don't see Turtle Graphics, it's because you haven't got the turtle loaded on your calculator or your computer, and you need to make sure you do that. We also need to load the turtle library, so I click on this first one from Turtle Import. And now I have the turtle library and all the commands that come with the turtle. And again, they're really simple to access. Menu, More Modules, Turtle. We're going to move. We want to go forward, and I'm going to pick a nice arbitrary number like 100. When I'm coding in Python, make sure you get to the end of the line before returning, otherwise it creates syntax errors and not, happy things go on. Well, that sends my turtle forward, and now I need to turn it 90 degrees. So I come back in here to More Modules, Turtle Graphics, Move, and I want to go left 90 degrees. Okay? And you can see that's in degrees. Turtle will also respond in radians. Cursor to the end and press enter. Now I can duplicate that 3 more times to get my other sides, but I want to be efficient in my coding. So what I'm going to do is select it. Those of you with the calculator, you can hold down the shift key, and with your cursor you can drag it over the text that you want to copy. And just like you do with your computer, you can do a Control C to copy, put your cursor where you want it, and then do a Control V. There you go. So I want to do that just a couple more times, so I'm going to paste that in there. And this is a very simple code, and even small children can go ahead and figure out how to code that and get that in there. All right, to get this to run, we're going to go Menu, More Modules. Oh, wait. This is a Python program. I don't need to go to Turtle Graphics. There's a command up here in Python to run. You'll see that mine has a shortcut called Command R. Well, Command R is native to a Mac computer, which is what I have. But on a PC, you'll probably see Control R. So either selecting this one or the shortcut Control R would run the program, and this is what it looks like. Okay, very simple to do. All right, I'm going to press Escape here. Let's show those folks who have the TI-84. Okay, here's the TI-84 CE, and I'm working on the emulator right now because it's a little bit easier to do that. But you can do the same thing by loading these programs from the TI site onto your calculator, especially these two called Turtle and Grid. Okay, they have to be in your apps, in your library, so that you can use them. Once you've got them there, we're going to go Program, Python, New. Now, these commands at the bottom right here respond to the function keys up at the top. So if you ever see them at the bottom, you can see the third one in is New, so that would be my zoom. And I'm just going to call this Square. Well, it'd be helpful if I spelled it correctly. Okay, yeah, I teach math, not spelling. That's pretty close. Okay, then I'm going to select OK. And there I am. I'm in the editor here. But just like we had to do with the Nspire, I've got to load the library. So that's done with functions. That's my first key right here, my first function key. Over here to modules. And you'll see there's a bunch of other stuff that's here, but because this hasn't been loaded on my calculator yet, I have to go to add-on. And because that menu is at the bottom, we click there. And then you can see, oh, there it is, Turtle Import. And once I bring that in, there's my library, and I can go ahead and write those commands. Now, I'm not going to take time to do that, but let me just show you what it would look like if I had it. So I'm just going to pull these from the files. I previously loaded this one called Demo, and there it is, drawing that square, just like we did on the Nspire. Okay? So either way works very, very, very well. I'm going to continue running this one on the Nspire, but you could do the same thing on the 84. My problem here is, well, let's see, let's get back to my slide. Okay, this is what it looks like on the Nspire. This one, I've abbreviated my code by making a loop so that I can have 16 sides. And I have to work out how I want to turn those. This is where this activity is great for kids. Have them build a square, have them build a triangle, have them build a hexagon, or a 16-sided figure, and they have to figure out how they turn that and how many degrees that has to go. And they also have to figure out how to get it in the window. Great thing to do. Here's what it looks like on the TI-84 when you get that code. Very, very similar running that there. Okay, what I want to do though is I want to put my circumscribe my polygon, and then I want to draw a diagonal. This is the code to do that. Let's show you right here. So as I pull that up right here, here is my code. Now I'm not going to talk so much about Python code, but it was pretty easy to get. I mean, it's you're going to have access to these codes when we're all done. And by the way, the best place that you can code, the best form of complimenting somebody on coder is to plagiarize their code and then organize it the way you want to. And so we'd expect you to get this code and then change it so that it looks pretty for you. Okay, so there's that code. This is this particular one right here. Whoops, sorry. This particular one right here is actually going to draw that diagonal. So let's do Control R and show how that works. I've hidden that triangle, that turtle, so that it'll run a little bit faster. Okay, so there's my inscribed circle and also my diagonal. When I go back into here again, looking at my code, This is the stuff that I want my students to figure out. And I've remarked that. The hashtag right here is the remarks. And I put that in there so that my students will know this is what you have to figure out. And again, some of them are really good at the calculation and figuring out what to do with that. And others are going to just play, which is what we want them to do, is to play and to experiment. Okay. This Turtle Python is a great place to get started. Once you get that, you can build other programs and add color and other polygons and so forth. I mean, it's fantastic. So fantastic. Anthony, you've got something to show them about how we use Turtle Python to figure out our pi.
Anthony, don't forget to unmute yourself.
Thank you. Can you hear me now? That's good. Michael, did you notice, are there any questions that should be addressed in the chat? I didn't notice any recently, but just want to, before we buzz on.
I think we're good.
Okay, great. So here we go. I got a little pause for a trivia break. Who used polygons to approximate pi? Your options here are Pythagoras, Newton, Archimedes, or Leibniz. And well, the fact of the matter is, I don't know, maybe all of these guys use polygons to approximate pi, but we certainly want to talk about Archimedes right now because of this next activity. There's something called the method of Archimedes, which is a way of approximating pi. And by the way, the method of exhaustion was not, he was not the first person to employ this method. But basically what it comes down to is finding a number that's a little bit smaller than pi and another number that's a little bit bigger than pi, and figuring out a way to get those numbers closer and closer to one another so that you can get a pretty good read on where pi is using sort of rational approximations. So what he did is he came up with the perimeter of polygons, which had ever more sides. And of course, as you increase the number of sides, you end up with something that looks closer and closer to a circle, and whose perimeter is closer to the circumference of the circle. So visually speaking, this is roughly what it looks like. Of course, if we go with a six-sided hexagon, the little one inside is called, it's inscribed in the circle, and the larger one is circumscribed outside the circle. And as we increase the number of sides, you see that those shapes have a perimeter that gets closer and closer to the circumference of the circle. So we're basically going to use this method. So I'm going to fire up my TI-Nspire, and I also created a little bit of code. Now, if you aren't into coding, or you haven't been coding in Python yet, or maybe you haven't coded for many years, I don't want you to be intimidated by any of this. If you read it, it's actually fairly straightforward. And I didn't know this until I started coding with the Nspire, but it's actually pretty easy to use. You probably saw Corey just flipping through the menus, creating the different bits of code. It's menu driven, so you don't have to worry about what's the syntax or any of that. Whenever you see these grayed out lines with a hashtag at the beginning, that's a comment meant for the humans reading it to understand roughly what this next bit of code does. And it's actually pretty readable. Like if this pen up, we'll go to a particular set of coordinates, or pen down. There's a for loop. You can see when it's going to drive forward, when it's going to turn left. So it's actually kind of, let's see, but Corey mute. Oh, I see. Okay. So, yeah, it's kind of readable, and would love for you to play around with it. So the only difference between this and the code that Corey was running is now we're going to basically do those polygons twice, one for the inscribed and one for the circumscribed polygons. So I'm going to run this. Here we go. And right now I've got an 8-sided octagon. The red one's inscribed. The blue one's a little bit larger. When it's done with the blue one, it's going to draw a circle for us that just touches each of those polygons. And when I'm finished with the code, it's going to tell me how far it drove with the red ink and how far it drove with the blue ink, or at least it's going to figure out the ratio of that compared to the diagonal straight across. And it seems like pi has to be in between 3.06 and 3.31. It's not, it's not a great read on pi, but it's pretty good. Of course, we can increase the number of sides. This one's going to be 16 sides, so I'm doubling the number of sides. I'll run that again. And as I was doing this, of course, I had to figure out how far it needed to drive forward for each of those red sides, and then how much it needed to turn. Now, the turn angle was kind of easy, but I had to do a little bit of trigonometry to figure out how far I wanted it to drive forward so that it would just nest inside the circle. And so that got me thinking, oh, by the way, what was that? This time the ratio was a little closer. It's between 3.12 and 3.18. Of course, we know the punchline, but kind of neat to see it getting closer and closer. Now, so as I was messing around, let me just zoom in on this a little bit. I'll put it in computer view. And anyway, so as I was doing this, I thought, okay, well, I could really come up with a teeny bit of code that's going to calculate how far to drive forward for each of these red sides, and really just use the same calculations I had been doing all this time. So that's really just using the cosine law, and I figured out how long side I is, the red side of the side of the red polygon. And then I also had to calculate the length of side C. That was a little easier. I was just using primary trig ratios. And the only reason I needed to, I had to find, it's not exactly the radius, but I needed to find this length, capital R, so that I could tell it where to start driving when it was drawing the blue polygon. So that's so those three calculations are what I needed. I'm just going to zip back into handheld view here. And so when I did that, so here's a bit of code that all it does is calculate those three numbers, okay? And I can tell it any number of sides. I've still got it on 16 sides right now. And as I run this code, it's basically going to say, okay, so for the small polygon, you're going to drive forward 39 units. For the larger one, each side is going to be 39.78 units. And the angle you have to turn at each of the, oh, sorry, the length R, I mean, is 101.9. Angle you have to turn is actually quite a bit simpler. It's really this angle here in the center is the same as the turn angle. So once you realize that, you realize all I have to do is take 360 degrees and divide it by the number of sides that I want. So anyway, so once I did that, I thought, well, why don't we just make some code that'll do any number of sides? Right now, I've got it doing 5 sides, which is kind of weird that we've got an odd number of sides, but this, these formulas are going to work for any number n. So let's give this one a try. Of course, we're going in the wrong direction now. We're coming up with less sides than before, but I just really wanted to noodle around with one that had an odd number of sides. And there we go. There's our inscribed and circumscribed polygons, pentagons around the circle. And it's a very bad read on pi. It's between 2.9 and 3.6. But of course, I could put any number I want in here. Be careful, don't put in a number that's too big. First of all, you won't be able to tell the difference between your polygon and the circle itself. But it's also a little bit slow. So I'm going to do 25 just for fun here. And I promise this is the last one we're going to take the time to do. Corey, I heard you saying that you made the triangle disappear to make it a little faster. I don't know why I didn't think of that. Now I want to go back and change my code. Take that triangle off.
Yeah, it's just a turtle hide.
Yeah, I'll try that. So this right now, you can see that the red and the blue polygon are so close together, they're really going to sandwich the circle pretty closely. And when it draws the black circle, it's actually going to make even that blue one mostly disappear. So there's the circle on top of it all. And there's the read we have on pi based on 25-sided polygon is it's between 3.13 and 3.16, we'll call it. But of course, if we have the time and a faster computer, and if we keep the triangle away, we could do even better than that, right? Oh, wait, not the preview to what's coming. Now, speaking of what's coming, so when I was in my second year of teaching, this is one of my very first teacher gifts. One of my students bought me this lovely book. It's actually really fun. It's not a very thick read. It's called The Joy of Pi. And it's probably not in print anymore, but if you can find a used copy of it, I highly recommend it. It's a lot of fun. And so when Corey and I were noodling around coming up with things that we wanted to do that related to Pi Day, I went and found this formula. And I really like it because it's just such a simple formula. It's just basically multiplying a sequence of fractions. First, we start with 2, which of course, as an approximation of pi, 2 is a terrible approximation. But if we multiply it by 2 over 1, then it goes to 4, which is ever so slightly better and ever so slightly bigger than pi. And then we multiply by this fraction 2/3, which is less than 1, so it makes it smaller. And it makes our approximation 8 over 3, which is a little less than pi. And as you multiply the red fraction, it gets to be too big. And then the blue fractions makes it too small. But what you end up with, of course, is a converging sequence. And it gets closer and closer to pi. And if you extend that pattern to infinity, then you will get to exactly pi, which is pretty cool considering how simple that sequence is. So hey, that seems like something I could do with some code really easily. So again, pulled out the Nspire and did a little bit of code inspired by that formula. And I'm not gonna spend a lot of time on this, but you see it's really simple code. We start with defining p at 2. I've given this one, I'm gonna do 500 steps, we'll do 50 steps, that's too much. You see that if basically this is saying if the number in our index number n is even, then it's going to multiply by this fraction. And if it's not, then it must be odd, so it's going to multiply by this fraction. And I put in a tiny bit of unnecessary code just to slow the sequence down. So I'm going to show this to you. This is the first 50 factors multiplying to get closer and closer to pi. And you see that it alternates between numbers that are bigger or smaller than pi. And after we run that 50 times, we can approximate that pi is between 3.1 and 3.17. So let's try that again, but now I can make it, of course, any number. So, any number of steps. So I'll bump it up to 500. And again, you'll see as I run it, the first 10 steps are really slow, just so that you can see what's happening. It gets to be too big, too small, too big, too small. And then it's going to buzz through 500. And as it does, you notice that after a while, the first couple of digits are hardly changing. And we could keep going. But right now, we know based on the Wallace product, that pi must be between 3.13 and 3.144, I'm going to call it, which is pretty good. And of course, we could keep going. By no means is this the most efficient way to calculate pi, but I like how simple it is. And then I thought, it is really simple. I don't actually need, well, here, I'm going to jump back to the PowerPoint. I don't actually need a program for this. Oops, I think I might want to jump past this. Oh no, did I put this in the wrong spot, Corey? Do I have a slide here? No, I don't. No, I'm stealing Corey's thunder now. Let me just see. I think I've got a slide in the wrong place. Oops. Okay, well, anyway, I was going to, I think we lost the slide somewhere as we were making changes. What I did here is just create a tiny bit of detail in a spreadsheet. Here we go. Rather than coding, if you're not into coding, you might go, okay, spreadsheets I get. And it really took me a few minutes to put this together. I wanted to sort of create that sequence of fractions that I want to multiply over and over again. So first we multiply by 2, and then we multiply by 2 over 3, and then 4 over 3, and 4 over 5. And you might notice that these fractions are, first they're bigger than 1, and then they're smaller than 1, and bigger than 1, and smaller than 1. And if you look at the formula in the bottom of my screen, you might notice that I'm basically using alternate methods for creating the fraction. And all I'm doing is using the numbers on the left side and a slightly different formula, but they alternate. And so all I have to do is take this fraction and multiply it by my previous Wallace product. So I start with 4, multiply it by 2/3, and I get 2 2/3. Take that and multiply by 4/3, and you get 3.556. And multiply that by 4/5, and you get 2.844. And this is doing the exact same thing that my program was doing, but it's all happening in a spreadsheet. So that's kind of fun. Now, if I advance forward here, we can see what it looks like if I graph that, and you can see a converging sequence where alternate terms are either greater than or less than pi. And of course, the number that it's approximate, or the number that it's approaching, is pi. So I just put that graph in there, and you can see the dots are getting closer and closer. And then I thought, oh, here's the slide I was looking for. Anyway, then I thought, if we group these two fractions together, something kind of cool is happening. So 2 times 2, of course, is a perfect square, 4. And on the bottom, we have 1 times 3. And if you think about this in terms of difference of squares, you can see why the bottom number is always going to be 1 less than the 2 squared on the top. So if we have 4 times 4 on the top, on the bottom is 3 times 5. You can see we end up with 16 over 15. The next one skips 5 squared and goes to 6 squared. We have 36 on the top, 35 on the bottom. There's a neat lesson there about difference of squares, the fact that I was able to group those together. And now I can multiply by half as many fractions to get the same sequence, essentially. What's neat about doing it this way is these fractions are all a little bit bigger than 1, which means we're constantly taking our approximation of pi and making it a little bit bigger. But it does so asymptotically, and it gets closer and closer to pi. So I did this with the spreadsheet, same process. Of course, it really helps that I discovered I could do that 1 less for the denominator than what's in the numerator. Again, talk to your kids about why that is, difference of squares, etc. And then I just copied the formula. I mean, just letting the calculator do all the work here. And so when I graph this one, this is kind of cool. You can see that the approximation starts way down here around 2 and a bit, and then it just gets bigger and bigger and bigger, and it's always growing, but it never quite reaches the value that we're expecting it to become, which is pi. I thought that was kind of fun, and just a different way of looking at it. And Corey, you have the next trivia questions.
I do. Before I take that one, though, and we answer this trivia question, we went through the Turtle Python, and you can see how we can manipulate that. And then we went through some code. And many of you are non-coders, but you have to understand where we came from is we saw the Python on our calculators and thought, well, let's utilize that. That's good problem-solving strategy to do that. Now, this turtle, I think, in my mind, it lends itself great to doing the rover. So if you have a TI Innovator hub and you hook that to the rover, you can move that around the floor or the desk or whatnot and do a similar sort of thing, just like you did with the turtle. And I've done that in class, and it's so much fun to get that out and work with it.
Corey,
Okay.
I also got back into coding with Python because of especially the rover. But we're going to show you later where we can do some 10 minutes of coding activities in case you're interested and want to get into it a little bit more.
That'd be great. Well, all right, let's pause here and look at our trivia. Oh, there was one question about how close Archimedes came. I think he did 16-sided, but he didn't have Python to work with. So he was able to calculate that, and he got, kind of reasonably close. I think his was the 22/7 sort of thing when he did his. All right, so let's answer this one. Who popularized the symbol pi? Let's see. Was it Einstein, Euler, Descartes, or Fibonacci? Give you a couple seconds to go ahead and do that one. Okay, have you guys already seen my slides? Everybody's saying B. Yeah, which That's true. It is. It's Euler. And what happened with this is that he created Euler's formula, right? So if you're not familiar with Euler's formula, this is the coolest formula ever. Look at this. It's got E, which is the natural base. Yeah, thank you. I saw that comment about Euler popularized it, but it was introduced before. That is so true. This Euler's formula has E, which is that natural base. It has I, which is the square root of -1. It has pi, which is an infinitesimal. And then it has this, integer, -1. Well, what we want to do is just take this and solve for pi. So some of you are in the pre-calculus and doing this sort of thing. Since it's base E, we're going to take the natural log of both sides. And at this point, you can see I'm going to take the natural log of -1. And all of you should be really bugged. I mean, I tell my students, I'm sorry, it's asymptotic at 0. You can't get over to -1. But we keep on doing this, right? Using the properties of logarithms. I pull that exponent out front. The natural log of E, of course, is 1. So that when I solve this, there it is. Amazing, Well, wait. Let's find out what the calculator says. So I'm going to go over here and put it on my Nspire. So here's my control divide, and I want to do the natural log. Here it is, natural log of, let's see, -1. Make sure you use the negation key here. And down below here, I want to put in I. Now, I don't want this letter I. Rather, I come to where it says pi. And you can see there's a whole bunch of shortcuts here, and one of them is I. Now, this is on a CAS calculator. And the CAS knows pi, which is amazing. Even the calculator knows it. But wait, it gets better. Let's take a look at the 84. We'll do the same thing. If I do alpha x, which is my fraction key, and do my natural log, here it is down here, natural log of -1. Again, make sure you use the negation key. We'll close up my parentheses because I want to be really good here. And then I don't want to use the letter I in here, but there's this one down here by the period that if I go second period, it will put in I. Now, right here, it should give me an error, right? Yeah, because that's what we're all expecting. But if I go into my mode, and I change my mode from real to a complex one, come back in, I'm just going to cursor up and grab that, press enter. Whoops, that's 2 of them. I don't want 2 of them. We'll just cursor up and get the one. There we go. And press enter. Look at that. Yeah, this is with the TI-84, and it approximates pi. I thought that was fantastic. Yeah, hail to Euler for figuring that out. Okay. Well, Anthony and I were thinking about other things that we might be able to do with Python, and I thought, how about, well, since I've hooked up my innovator to my rover, wait a minute, that innovator hub creates sounds and colors. What if I just create a song on the innovator? So that's what I did. Let's take a look at the code. Here is my code. I'll open that up. Now, again, I haven't had a lot of experience with Python, but I'm a little bit musical. So I created one with a C scale. This C4 is middle C, for those of you who had some musical training. And then I go up my octave, and of course, I have 10 digits of pi, so I have to, repeat some. And then I said, well, maybe I want an F scale. So an F scale, some of you will know, has a B flat in it. So this is how we do a B flat. I'm thinking with students who are musically inclined, we could do a E flat scale, a B flat scale, a G scale. Yeah, G, you can go ahead and put in sharps. And then I went out to ChatGPT, and I said, okay, I need some digits of pi, because I was going to tell you that I memorized these off the top of my head and put them down, but there are 100 digits of pi, and I'm old, so I only go to about 5. My students can go about 20 or 100. They're really good. My code down here is really simple. Just a for loop tells me I'm going to go 100 digits. I'm going to print that out, and this one sound note, I'm going to have to do that. Now, for those of you who want to run this, you'll notice that my REM statement at the very top, make sure you hook up the Innovator Hub, because if you don't do that, you're not going to hear it. Lucky for us. I recorded it. So let's listen to Pi. Okay, it's kind of faint. After about 25 or 50, it starts to get monotonous, right? Okay, trust me, I got 100 digits of pi in here, but it keeps right on going. What I've done is I just assigned a value, the same value to every note. And that doesn't sound all that good. What would be better is if I actually made a song with it. Well, fortunately, somebody thought of this before. So Phil Tulga, out on YouTube, and you can get the address right there, he took the song and he actually sings it. You don't want me to sing it. So I played it on the piano. Yeah, I'm not a great pianist, but I played it on the piano and it sounds like this. Yeah, those of you who are musical there, you realize that I didn't take the repeat on that. But he goes out to 100 digits of pi and he's singing that. I would like to give this to students to say, go ahead and take that, and you don't even need Python. You can go ahead and create the music, and you can change the notes. You can put in eighth notes and rests and change the timing and all sorts of things and make that song for pi. That was just so much fun to go ahead and code and do. Something a little bit different. Okay. Next one. Which digit occurs the most in the first 100 digits of pi? Is it 2, 3, 8, or 9? Go ahead and we'll let you vote on that. Yeah, I think this is going to surprise you. Yeah, I see a lot of 3s coming in here, but the first one actually that came in was correct. It was 9. It was 9. Now, you could get your digits of pi and line them up and start counting, but I said, let's get Python to do that. So I borrowed the same list that I got from ChatGPT, and I put that list in, and I made something really simple. So here's my counters. It just says, if you encounter it, go ahead and start counting. Just, really simple code to get that to go. Let's show you that it actually did it. Control R, because remember that's how we run this thing. And sure enough, I got 14 9s out of 100 different characters. Well, I got thinking about this. What an activity, fun activity this could be to write. And kind of like Anthony, I said, let's put this in a chart. So here's the digits, here's the occurrence, and then let's chart it. Let's see what it looks like. So this is the first 100 digits of pi, and I was looking to see if there was some sort of a pattern. And it just so happened that there was. I get the constellation Cassiopeia. Okay, I know that's another dad joke, but that's what you get with math, math teachers and dads. But anyway, that was fun. Well, I was looking at my code and I thought, oh, Corey, that is so long and it's not very efficient. So I actually took that code and I said, ChatGPT, tell me what to do with my code. And so it came back and it gave me some code, which did not work on my calculator. So, but it inspired me to do other things. First of all, you'll notice here that I put it in as a list and there are no commas in this, or not as a list, but as a string, and there are no commas in that. And it just read that string. That was a lot more efficient. You can see this code was abbreviated. Folks, when you get into Python, that's what you do, is you write the simple stuff, and then you think, how can I improve that? And you do the same thing with your students. You think, what can we do to make this better, to make it more efficient. Good problem solving when they put that together. So when I ran this one, let's do this real quick. Here's my Control R, and notice I get exactly the same results when I get this one put together. Okay, so fun stuff. You can go ahead and do that. Then I went to ChatGPT and I said, all right, why don't you show me 1,000 digits of pi? And there they are. Oh my gosh, there's so much pi in there. And I wanted to know how many digits of pi have been calculated. I had to ask Anthony for the spelling of Google because I thought it was going to be, you know, the same as the Google engine, but it's not. Nope, this is how it's spelled. Yep. Yeah, you'd think it'd be Google, right? But this one actually is 202 trillion, and it happened just this last year. And they'll probably go ahead and calculate this over and over again to do that. I am not going to put that in my calculator, nor am I going to write a Python program to do that, because I'm an old guy and it probably won't finish in my lifetime. But, you know, there you go. Anthony, tell us about some of these other activities.
How about now? Am I still muted?
Yep, you're on.
Awesome. I wanted to drop something in the chat, but I don't know how to find the chat anymore. I'm not that used to WebEx. Oh well, that's okay. I was just going to drop that link that's on the screen in the chat, but you can get it later from the presentation. So here we go. I'm going to go open up my browser. We're going to go to the TI bulletin board blog, and the very first item here is Celebrate Pi Day. Corey and I, when we were noodling around coming up with ideas, one of the places we went with here, oh gosh, oh, here we go. So I'm going to click on this link and just want to show you a few things because there's some pretty cool stuff here. The very first activity is the one we opened up our session with. This is the one with the beautiful, delicious picture of all the pies, and it's got key press suggestions for students, which I find really helpful. I did a slight modification of this activity. If you want, my modification is going to be in the Google Drive that we share with you later. But really worthwhile. I highly recommend it. If you're more of an Nspire user than a TI-84, there's a couple of specific Nspire activities that you might find interesting. This one compares pi to roots, and this one looks at why pi tells us what the optimal size is for biological cells, which I think is kind of cool. If you or your students are looking for more of a mind break, you can download coloring pages related to pi. You can even get stuff to create your own swag, whether it be t-shirts or printing on cups, or if you like to make your own stickers, there's files and templates for you to make your own. All kinds of great stuff. There are more Pi Day webinars going back for years. I enjoyed watching some of these from the archive. Highly recommend it. But you know, I know that that Corey and I have been sharing a bunch of activities, and some of them were related to coding. And we are aware that you know, some of you might not be into coding, or maybe not into coding yet. So I just want to remind you that, you know, for most of my career, I taught with with TI technology, sometimes 84 and then 83, and then more recently the Nspire. But I'm just going to open up a link here. There's a website on, or there's a TI website. If I can figure out how to click the link. Now, you know what I want to do? I want to put this in. I'll put it in the chat in a minute. But right now, I'm just going to open up one of them. This is called 10 Minutes of Code. And I'll bring it down here for you. So this is the Python version, but there's also a 10 minutes of code for the TI-84, and that's also Python. And there's even a TI-8384 that's not Python, it's just for TI Basic. So if you have an older machine that doesn't have the Python chip, these 10 minutes of code activities are fantastic. And when I was relearning how to code, or when I was learning how to code in Python, I went through these, and you just give yourself a little bit of time on an idle Sunday afternoon, and you can teach yourself Python relatively quickly, and it's really gratifying when you get, that little bit of code working. So I highly recommend it. If you feel like maybe that was a part of our presentation that you weren't completely understanding how we did it, or you were thinking I couldn't do that, give yourself a chance and try this out. So these are all things that we found on the TI website. Highly recommend you give it a try. And at this point, we're going to pause again and ask if anybody has any questions. I did appreciate that one person who knew that while Euler did popularize pi, that Euler was not the person who came up with the idea of using the Greek letter pi as a symbol for that number. But maybe if it wasn't for Euler, we wouldn't have heard about it.
I see a comment here on the chat about reading some of those coding lessons carefully. I'll testify to that. I pulled some of those out. But again, I think the purpose of those lessons is to inspire you to write your own code and to use that just as a structure. But you want to add things. And students are really creative. I've used these activities in my classroom and just given them the sheet and I said, go for it. And they'll find those mistakes. That happens in life. But then they say, this is how we fix it. And they share it with each other. And the problem solving comes out. Oh, it's such a wonderful activity.
I popped in some links in the chat. If any of you want to try the 10 minutes code, there's 3 different ones there. One is for the Nspire Python, one's for the 84 Python, and one is just for coding TI Basic on any of the hardware that doesn't have Python. And I'll just remind you that if you have the emulator software, if you have the teacher edition software, then you can use Python on that as well.
Anthony, show them the last slide there for how they get the presentation.
Good idea. Thank you. Do you want to get now? Is this is the presentation slide, or is it this the entire folder, Corey?
This gets all the files.
Yeah.
We've added some extra materials as well. I'm going to paste the little bit.ly in there so that you have that in case you don't want to scan the code. But you get the presentation, you get the files that we showed you, the code, the whole 9 yards.
There's even some files in there that we didn't have time to present. You can noodle through them. Michael, are you there?
I am.
I'm excited. I want to see who's going to win this thing.
All right. Well, tonight our lucky winner is Yasmin Sandir. So Yasmin, congratulations. Start thinking about which graphing calculator you'd like to receive, and I will be reaching out to you soon to get some information. I know some of you were asking about the documents and if the link that Anthony and Corey sent out is working. That's great. I also have my own link, which includes my documents as well as theirs. So if that would be easier for you, feel free to grab that. You'll also be getting a follow-up email within a couple days, and that follow-up email will contain links to the recording, the documents, and the certificate of attendance as well. And if you're watching this on demand, copy that link into your favorite browser to receive your certificate. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Feedback guides us as we plan our future online events, and it really, really helps us to hear from you. So please take a minute and let us know what you think went well, and what are some things that we can improve on, and what are some things that you'd like to see in the future. Thanks so much to Anthony and Corey for all the time they had putting this together. I know that it was a lot of work for them, and just really appreciate all the time they spent.
Thank you.
And thanks to everyone for joining us tonight. We hope to see you back online next week. Next week, we're going to focus on AP pre-calculus, and we are going to be looking at rates of change and polar functions. So if that is something that interests you or may interest someone that you know, we'll see you next Tuesday. Have a great night.